Hey everyone, it's me, Dr. GB. So I've gotten several requests to walk through the thermodynamics quiz. So I will go ahead and I will do that now. Okay, so we will walk through questions 1 to 7. Alrighty, so for the first question is, what is the Kp of this reaction at 220 degrees Celsius? All right, so we got this reaction, the decomposition of silver carbonate into silver oxide and CO2. All right, and so what I saw here is we saw Kp, and so a lot of people saw, I need to interconvert between Kp and Kc. No. So if I explicitly ask you to interconvert the two, so if I give you one and ask you to compute the other, you have to, but you can use either one or the other in the equation of delta G equals negative RT ln K, all right? So there is no designation. This can be P or it can be C, all right? It's just if I were to give you this in molar and then ask you for Kp or vice versa, you would have to do the conversion, but because I've given you the value in ATMs or pressure here, you can go ahead and use the K sub P, all right? So to do this, we have to find the Kp. So to start, let's write out the equilibrium expression for this, all right? So our Kp is going to be the partial pressure of CO2 gas raised to the 1 power times Ag2O. Oh, wait, that's a solid. Nope. Okay, so CO2 raised to the 1 over Ag2CO3 to the 1. Oh, wait, nope, it's also a solid. Okay, so our Kp is just plain old CO2, okay? And that may seem, or rather, I have CO2, actually, I have a concentration there, but again, this is a Kp, so it's the PCO2, excuse me. So what that tells us is the Kp of this reaction is equal to the pressure of CO2, or it is 1.37. All right, so that answer is going to be 1.37. Okay, so again, this is one where it seems like it's tricky, and it is tricky. But again, quizzes are going to be a little bit trickier than the questions you're going to see on a mini review. Okay, so let's do the next question. What is the delta G for this reaction at 220 degrees Celsius? You must include units in your answer for full credit. Okay, so again, delta G, assuming we're at equilibrium, which we can assume we're at equilibrium because we're using our K, all right? So delta G naught is equal to negative R times T times the natural log of Kp. So, all right, so first things first, we're going to do is we are going to determine our R. We are going to use 8.314 joules per mole Kelvin. All right, and then our temperature, we've got Kelvin, so our temperature needs to be in Kelvin. So we have 220 degrees Celsius plus 273 gives us 493 Kelvin. Okay, so solving for delta G, we get delta G is equal to negative 8.314 times 493 Kelvin, so joules per mole K. All right, so our K's cancel out, times natural log of 1.37. Okay, so we get negative 8.314 times 493 times natural log of 1.37. Okay, and that gives us negative 1290. Now, I stop here because the biggest thing I saw on the quizzes was confusion with units. And so if you just go and submit 1290, you are going to get points off because I don't know 1290 what. So if we look at our units, we've got a joule here in our unit. We got a joule here from our R, and we've got a per mole because we didn't multiply by any moles. So our delta G naught is going to be negative 1290 joules per mole. Also acceptable is converting this into kilojoules. So negative 1290 joules per mole times 1 over 1,000 joules per 1 kilojoule gives us negative 1.29 joules per mole. Now, for these, I will accept joules per mole. I will accept kilojoules per mole. I will also accept plain old joules and plain old kilojoules. But one thing I need to say now is I went ahead and I gave everyone credit back if you missed it on the mini review or on the quiz. However, joules is capital J. Joules is not lowercase j. Secondly, kilo is a little k. It is not big K. Big K means equilibrium. So make sure when you're writing out your answers, you are capitalizing your J and you are lowercasing your K. All right. So it will not let me enter in like different cases, but it will recognize different cases when you type them in your answers. All right. So, and the reason why we have to specify our units is because we had 1,290 joules per mole and then negative 1.29 joules per mole Kelvin. So for instance, or joules per mole, if you tell me negative 1290 kilojoules, that's wrong because and if you tell me negative 1.290 joules, that's also incorrect. So it is important to make sure that you're keeping track of your units and that you check them at the end. Okay, next question. So a lot of people, again, were super irritated about this question because what I did here is, again, this was a tough one in that I gave you the delta H of formations for the silver compounds because those are not found in the back of your textbook. However, CO2 gas is found in the back of your textbook, and I want you to have that experience of going in your textbook and consulting it. So what you do is you go into your textbook and you find, okay, here I am preaching about units and I'm not including the unit, so apologies here. All right, so you've got your values for silver carbonate and silver oxide, and then if you go and you look up CO2, CO2 is negative 394.4 kilojoules per mole. Actually, I got that wrong. That's negative 393.5. Whoops-a-daisy there. 93.5 kilojoules per mole. Alrighty, so the way we would set this up is the sum, or excuse me, our delta H of reaction is equal to the sum of the number of moles times our products times the delta H of formation for the products minus the sum of our moles of reactants times the delta H of formation for the reactants. Now, there's some confusion about what this calculation looks like. So I'm going to go ahead and I'm going to write it out, okay? So what this would be is the moles of CO2 times the delta H of formation of CO2 plus the moles of Ag2O times the delta H of formation for Ag2O minus the moles of Ag2CO3 times the delta H of formation of Ag2CO3. And this is a blast from the past from our thermochemistry section. All right, so our delta H, and that shouldn't be there, our delta H of reaction is equal to 1 mole, so I'm going to put parentheses because we have two components. 1 mole times our delta H of formation of CO2 is negative 393.5 kilojoules per mole plus 1 mole of Ag2O times negative 31.05 kilojoules per mole. All right, our moles cancel. Minus 1 mole of Ag2CO3 times negative 505.9 kilojoules per mole. And again, our moles cancel out. So what we get is negative 393.5 plus negative 31.05 gives us negative 424.55 kilojoules per mole, or not mole, we multiplied away our moles, all right? And so this is the sum of our products, okay? Minus negative 393, nope. Sorry, y'all. It's after 6. Dr. GB's brain is, woo, out there. 505.9 kilojoules, okay? So effectively, we have negative 424.6 plus 505.9, and that gives us 81.6 81.35 kilojoules. All right. So our answer for this is positive 81.35 kilojoules. Okay. So the question is then, what is the delta S for the reaction at this temperature? Now, there was a lot of confusion here about standard state, because what I told you is if you look up in the back of the book and you go, oh, delta H RXN, and if you, that measurement was taken, all right, that measurement was taken at a, this was measured at 25 degrees Celsius or 298 Kelvin, all right? However, just because the delta H reaction was measured at 298 Kelvin, that doesn't mean that the delta H reaction is going to change a lot with temperature. In fact, this is why if you go and if we take the natural log of our equilibrium constant and we graph it against 1 over temperature, all right, and let's say we're going up here, the slope of this reaction is negative delta H over R, and then the intercept, I actually think it's supposed to go the other way. Well, it depends on whether or not it's exothermic or endothermic, but the intercept is the delta S over R. Okay, so what this tells us is that our natural log of K and therefore our delta G changes with temperature, all right? So delta G naught changes with temperature. However, for every natural log of K with T, we have a different delta H, or different delta G, but the delta H comes from the slope or the change. And then the delta S comes from that intercept. So what that means is all those delta G's have the same delta H and delta S. All right, so what that tells us is delta H and delta G and delta H and delta S do not change a lot, at least with temperature. All right, we make the assumption that the changes that occur with delta H and delta S with temperature are so small that we can ignore them. But that's not true for delta G, alrighty? And so delta G is temperature dependent, delta S and delta H are not. So for this, we have our equation, delta G naught is equal to delta H naught plus T delta S, all right? Even though we're using our standard ones, we have, so for instance, what would happen here is if we were to go in the back of the book and we were to look up our delta G's of formation at 298 Kelvin, we could only use those at 298 Kelvin, all right? We could not use these for 220 degrees Celsius. However, we can use our measured delta H and our delta S values for an equation at 220 degrees Celsius, and that's exactly what we're going to do here. So we know that at 220 degrees Celsius, we have, and I'm actually going to go ahead and I'm going to erase a bunch of this in the interest of mapping things out, okay? Alrighty, because I want to go ahead and I actually want to write out this calculation nice and big because there's a lot of stupid, sticky little stuff here that we have to think about. So we have delta G equals delta H minus T delta S. All right, so we know delta G. We know that delta G is 81.35 kilojoules. All right, we know that delta H is negative 1.29 kilojoules. And then we have to, so we are solving for S. So plus 493 times delta S naught. So to solve for delta S, we are going to take delta G naught minus delta H naught over T, or 81.35 kilojoules plus 1.29 kilojoules over 493 Kelvin. And that gives us an answer of 0.168 joules per Kelvin, all right? or excuse me, kilojoules. Again, the importance of units, y'all, they matter. Kilojoules per Kelvin. You could also report this as, multiply that by 1,000, 168 joules per Kelvin. Okay, so delta S, we're always going to be in joules per Kelvin or kilojoules per Kelvin. And again, that's because delta H is equal to delta S over T, or our joules per Kelvin. All right, and so that's why we multiply T times delta S to get rid of that per Kelvin in the denominator. All right, so we've got 0.168 kilojoules per Kelvin or 168 joules per Kelvin. And again, for every temperature, we have to calculate a new delta G naught, but we can use the same delta H naught and the same delta S naught every single time. I'll go ahead and I'm going to write it out. So here comes the fun part. What is the delta G naught of this reaction at 25 degrees Celsius? You must include 2 units for full credit. Okay, so there are 2 approaches you could take to this problem. One is that you could look up the delta G of formation. And in fact, if you were to go and you were to look at the delta G's of formation, or you could go and do that. So you could use the delta G's of formation. The other is you can plug in delta G naught equals delta H minus T delta S. No, you can't do delta G is equal to minus RT ln K. Why? Because equilibrium constants are going to change with temperature, and our Kp is at 220, so we can't trust that. So we can rely on our handy dandy thermodynamic parameters again. So delta G naught, so now we're solving for delta G, is equal to negative 1.29 kilojoules, all right, minus, okay, 25, that's 298 Kelvin, times 0.168 kilojoules per Kelvin. Now notice, again, our entropy value here, it's in kilojoules, and it's a lot smaller than our value for enthalpy is. Our entropy values, if you look them up in the back of the book, they're going to be reported in joules, not kilojoules, so you have to convert, and that's because they look so much smaller because our entropy value is divided by temperature. All right, so, okay, so if we go through and we carry this out, we get negative 1.29 kilojoules minus 49.95, hold on, yep, minus 49.95 kilojoules. LOL, silly Dr. GB. Dr. GB did the wrong thing. She confused her delta G and her delta H, so we got to go back. All right. See, what happens with this program is I have the work on different pages and it pauses the video. So sometimes I get a little discombobulated, so I try to just remember things instead of checking, and that's how we end up in this mess. Okay, so delta G naught is equal to 81.35 kilojoules minus 298 times 0.168. Okay, so 81.35 minus 298 times 0.168. All right, so that is 81.35 minus 51.35, and that gives us okay, so I got a value this time of positive 29 or like positive 30. But as long as you are in the neighborhood of between 30 to 32 kilojoules, you should be good to go. And so one thing I've noticed is that small changes in like how many decimal places you use results in a different answer. Because we're working on like these really large numbers, like sometimes the changes, I'm still kind of working on my adjustments on what's an acceptable answer. So you might do the math right and then have it scream at you and be like, no, that's wrong. So like I go back and I double check those bounds. So if you're sure you've done it right, but the Moodle tells you it's wrong, I will catch it and be like, that seems close. I don't know why it marked it off. So don't panic. I am keeping an eye on going through these with a fine tooth comb. So the answer that I have on the Moodle is plus 31.39, but like I got things all the way from 30 to 32, so as long as you're in that 30 to 32 neighborhood for kilojoules per that, you're fine. Okay, so the next question then is, what is the partial pressure of CO2 at 25 degrees Celsius in ATM? This is another one that got a lot of people really confused. All right, so what happens here is we have delta G naught is equal to negative RT ln K. So we talked about earlier about how we knew the K at 220, and because we knew that at 220 degrees, the partial pressure of CO2 was 1.37. All right, we could determine that was Kp, but we could determine the delta G from that. But even if we knew the delta G from the book, we couldn't determine the K at that temperature because it was different. So we are taking problem 1 and we are going in the opposite direction for this, all right? So what we're going to do is we're going to find the delta G naught. So we have the delta G naught at 25 degrees Celsius, all right? And then we're going to take it to find Kp, and then from Kp, from the Kp, we can find the partial pressure of CO2, all right? So we're doing the exact opposite. So we've got 31.39 kilojoules is equal to negative 8.314 joules per mole Kelvin times 298 Kelvin times the natural log of K. Now, right off the bat, you notice, we've got kilojoules here and we've got joules here. So we have to make sure we convert that to kilojoules. How are we going to do that? Move a decimal over 3 spots. All right. We turn that into a comma. We have 31,390 joules. Okay, perfect. So we're going to solve. So natural log of K is equal to 31390 divided by negative 8.314, and that's joules per mole K, times 298 K. How do you know if you're right? Okay, we cancel out our Ks, our joules cancel out, and I guess we really didn't have to include our moles anyway. So we have no units. That's good. Equilibrium constants have no units. Now let's propagate the math here. 31390 divided by negative 8.314 divided by 298. Okay. All right, so we get natural log of K is equal to negative 12.67. Okay, so we want to solve for K. So the way we can solve for K is we raise e to the power of both sides. So we go e to the answer. All right, so e to the answer gives us K is equal to 3.15 times 10 to the negative 6. And if Kp is equal to the partial pressure of CO2, because it's the only gaseous part of equilibrium, well, then our partial pressure of CO2 is equal to 3.15 times 10 to the negative 6 atm. All right, there we go. So 3.15 times 10 to the negative 6 atm. Wonderful. That brings us to number 7. At what temperature in Celsius does this reaction change from being spontaneous to non-spontaneous? You do not need to include units. Okay, so here's the deal. So for this reaction, we have a negative delta G. All right, so we know it's always going, so we know that under these conditions, it's going to be spontaneous. But if we look at our delta H's, we have a positive delta H and we have a positive delta S, all right? So if you go back to that video where we talk about predicting spontaneity, based on the signs of the delta H and the delta S, you can predict whether or not the reaction will be spontaneous. So if if delta H is negative and delta S is positive, delta G will always be spontaneous. If delta H is negative and delta S is positive, or delta H is positive and delta S is negative, it's always going to be non-spontaneous. When delta H is positive and delta H is positive and then both of them are negative, that's when when temperature starts to be a concern, all right? So for delta G, so if we have a positive delta H and a positive delta S, the way that we would solve this is we want to find the point when delta H and delta S are equal to each other. All right. And so the way we're going to figure that out is we are going to go Okay, so when delta H is equal to delta S, that's when delta G is going to be, or rather, when delta H is equal to T delta S, that's when delta G is going to be 0, and that's going to be the break-even point. Because when now you're on the one side, delta G is negative and it's spontaneous. When you're on the other side, delta G is going to be positive or it's going to be non-spontaneous. So if we have delta G naught is equal to delta H naught minus T delta S naught, we set delta G naught equal to 0. So we get 0 is equal to delta H naught minus T delta S naught. Okay, so we rearrange, we get T delta S naught is equal to delta H naught. Okay, so we're solving for T, so we're going to divide both sides by delta S naught. All right, we get T is equal to delta H naught over delta S naught, which is equal to 81.35 kilojoules over, over rats. What is delta S? Aha, 0.168 kilojoules per Kelvin. All right, our kilojoules cancel. And then we have 1 over Kelvin for our units, and we get 484. We get 484 Kelvin. Now, you may be looking at me and be like, Dr. GB, 484, no. The quiz says it's 212. Okay. All right, so no. So what it is, and actually that's 484.2, fine. Okay, so that's in Kelvin. The problem is asking in Celsius. So temperature in Kelvin is equal to temperature in Celsius plus 273.15. So to find the temperature in Celsius, you have to have Kelvin minus 273.15. So the degree is going to be that minus 273.15, and that gives us 484.2 minus 273.15 gives us, okay, so my calculator, I'm getting 211.05. But again, honestly, as long as you're between 212 and 214 Celsius, we are okay. All right, so this is around 212 degrees Celsius. Okay, all right, so those are our answers for 2 to 7. Finally, why not? We're here. Let's just look at the last couple ones, which of the molecules have the largest standard molar entropy. So we had several rules in our videos that dictated the relative standard molar entropies of different substances. And one of those was the more complex the molecule it is, the more ways it can rotate and vibrate. And so we'll have a higher standard molar entropy. C is our most complicated, all right? So our most complicated, our complex, our largest molecule, so C would be the winner here. And finally, if we look at 9, okay, what's the deal with 9 here? So again, we have several different standards that allow us to make predictions about the entropy change of a reaction qualitatively. So on the left-hand side, we go from 2Na plus to 2O2 gas goes to 2NO gas, alrighty? This is going to be a positive change. Why, you may wonder? 2 things. Number 1, we're getting rid of a solid. And number 2, we go from 1 mole of gas to 2 mole of gas, all right? And when we see there's a reaction that increases our moles of gas, it's going to be a positive or favorable or an increasing entropy change. Let's look at letter B. Okay, we go to 4 phosphorus acid, which is a liquid, to pH3 gas plus 3 H3PO4 liquid. Actually, that should be aqueous. It's fine. Okay, so this one is also going to be a positive. Why? Because on the left, we have no gas, and on the right, we have a gas, all right? A reaction that increases the amount of gas, whether you increase the number of moles or whether you go from 0 gas to moles of gas, that is going to be a positive change in entropy. Okay, let's look at C. Alrighty. So we go CO gas plus H2O gas forms CO2 gas plus H2A gas. Okay, so we have the same number of moles of gas on both sides. And honestly, looking at this, there's nothing really that gives me tip what is happening. So this is going to be an instance where we have an NEI or not enough information, because that thing that we usually use, which is like how much moles of gas do we have, it's the same on both sides, and one doesn't have a solid and the other doesn't, so we really can't tell. And if we look at the bottom, we see the same thing here. we have on both sides, we have 1 mole of gas, and then we have 1 mole of solid, and then 1 mole of solid. So again, not enough information. We can't tell because our amounts of moles of solids and gases are staying the same on both sides. We really don't have enough information to make a call on that. Okay, I know this is a super long video, so I hope that this will help. Again, I'm not holding student hours tomorrow, but that doesn't mean you can't contact me if you have questions. I will be at my computer probably till around 3. So wish you the best of luck, and just contact me if you have any questions. All right, talk to you later. Bye.